all, what we showed in the last class was that if we have to find the state of stress at a point, that turns out to be a second order tensor. And if we know the components of the second order tensor, then at this point, whatever surface element we take, we can find the surface force given the state of stress. Given sigma ij, whatever angle at which I take my area, which will be the angle will be defined by the outward normal. So given the outward normal, I can find the traction force for that particular area. And the traction force, as we showed, its magnitude as well as direction depended on the area, but overall the state of stress stays the same. Okay? And then we showed that this, if originally my original components are x, y, z, I rotate them to x prime, y prime, z prime, then the components of the stress are related by this equation. And this equation will be the theme for today's lecture. And this part is from chapter 7 of the book. So I am straight away first skipping to chapter 7, and then I will come back to chapter 1 and 2, because this tells us some generalizations which I am going to use in the course. Okay? So this equation, as we said, and it's very easy to remember this equation. Of course, in this course you don't have to remember any equations. Everything will be given to you as formulas. Extra formulas will also be given. Suddenly you may find in the formula list E is equal to mc square. You may not need that, but you should know which formula is needed. So now the way to sort of see this is sigma in A, the way we have defined, it is always the old axis first and the new axis later. So if our original components are sigma Lm, and we have to find sigma ij prime. So we write first A Li. L corresponds to the first index of sigma Lm, the old components. I corresponds to the first index of the new one. Then I write Amj. So here in the second one, M represents the old second index of the old stress, and J represents the second index of the new stress. So this is how the transformation, at least a way to remember it. Not that this is how it works. So this is, and what are ALIs? They are the direction cosines. So A11 will be the cosine of the angle between 1 and 1 prime, and so on, x and x prime. And we'll work on this theme later. So now starting from this, then what we did was in the last class, we took an infinitesimal element and we derived the equation of motion for an infinitesimal element. Now for a rigid body or for a system of particles, you have seen this as sum of F is equal to ma. Newton's second law, Euler's first axiom. So we use the same equation for this, for an infinitesimal volume on which the surface forces are given by Ti, which we can represent in terms of sigma ij, and the body forces, we represent them as rho gi, forces per unit volume. So we do a force balance and we apply Gauss's divergence theorem, and we arrive at the basic equation which is valid for any material, be it solid, be it fluid, and it's a differential equation, so it is valid at each point. For each material point or each particle, this is valid, which is rho times vector A is equal to rho times vector G plus divergence of sigma ij. Okay? Is that clear? So this is the equation for which we call as Cauchy's equation. And now the difference in solid and fluid mechanics which will come, which you will see in this course, will be how sigma ij is related to either the displacement or the velocity. We have already seen this, that stresses in a solids are related to displacements, and stresses in a fluid are related to the rate of displacements. So that difference is what is going to come in, which will be the two parts of this course. Okay? Now, the last thing which I did, and for which I have added the full detailed derivation afterwards at home and put that on the board, is if we apply Euler's second axiom, which works out to be torque is equal to I alpha. I won't go through the details, but what I did here was, and I gave you a physical meaning of this, that if we have if on a small element I have a shear stress tau yx, and if I perform the moment balance for this element, then what I will get is there has to be necessarily a tau xy on the top face which will balance this, otherwise the element will keep on rotating. So if we have equilibrium, that means there is no rotation, then clearly we can see that there has to be a tau xy on the top face. So unless if there is a shear stress component like this, the element will keep on rotating. But what I have shown, and which probably did not come out in the lecture last time, was I take an infinitesimal element where now a lot of you asked me after the class that at the point of O, I gave the state of stress as sigma xx, sigma xy, sigma yx, sigma xy. So right now they are all 4 different stresses. Okay? Then on the face AB, I expanded sigma xx in a Taylor series. All of you are aware of a Taylor series or no? If you have to find f at x plus delta x, and you know f at x and all its derivatives of f. So what is f at x plus delta x? F at x plus df by dx times delta x plus d2f by dx square times delta x square by 2 factorial and so on. And if delta x is small, then we can ignore the higher order terms. So that is what we have done here to get the stress components on the face AB as well as on the face CD and all the 4 faces. So we have expressed things in a Taylor series. Now, if we look at the face CD, the outward normal points in the minus x direction. So therefore, whatever is the stress component, the positive component of that is the convention we use, will be in the negative direction. So doing that, what I did was first I expressed the stress component, and then I found the surface forces on all these elements. And then I performed torque is equal to I alpha. In the limit, delta x goes to 0, delta y goes to 0. So when I do this, and this is what I have written as detailed proof, this is what was added. So I do it on all the 4 elements, write the terms. Now, here I am not assuming that alpha is 0. So there could be rotation possible. Okay, earlier when I talked of equilibrium, we said alpha is 0. But now even if alpha is not 0, when I perform the moment balance, what I get is a term, the eventual equation turns out to be tau yx minus tau xy multiplied by delta x times delta y is equal to moment of inertia I times alpha. And the moment of inertia will be half times the mass times delta x square plus delta y square alpha. Now in the limit that delta x and delta y go to 0, even if alpha is not 0, the right hand side term goes to 0. Any doubt?
That is 1 by 12, right?
Yeah, it's 1 by 12. ml square by 12, whatever. Actually, that 12 doesn't make a difference, but it's 1 by 12. I hope I'm right. I'm not sure. I just, okay. So now here what will happen is in the limit delta x, delta y go to 0, you see that there are 2 terms on the left hand side which are multiplied by delta x, delta y. So there are at least 2 terms. And we have a third term on the right hand side which is delta x delta y to the power 4 or delta x to the power 4. So therefore the right hand side term irrespective of value of alpha will be small. And this gives us the relation tau yx is equal to tau xy. So the two complementary shear stresses have to be equal irrespective of what the material is. So it does not whether we are talking of wood where properties change with direction. But even there, if I look at a small point and I look at tau xy and tau yx on that element, they have to be equal. The only place where this will not work is if they are body couples. Then the body couples will be of the order of the couple multiplied by the mass of the element. And so there, if they will be of the same order as tau xy, then we may not, because then when you multiply by volume, it will be delta x delta y times 1, which is the same as the left hand side. If we have couple per unit volume acting on the body. And then tau xy may not be equal to tau yx. But at least for the purpose of this course, we will not count such situations. So tau xy, and if we extend it to 3 dimensions, we get the general relation tau ij is equal to tau ji. Now for those who are interested, there is a detailed proof for this for a 3-dimensional case using tensor notation. I will put it up, but I am not going to ask anything in the course. So this is just for those who are interested. And there we use a special fact that we talked of epsilon ijk. So if epsilon ijk is multiplied by a symmetric tensor, then the result is 0. And that fact is used to get the result. Okay? So I'll put that up. Those who are interested can have a look at it, but otherwise you don't need to look at it. Okay. So now let's start with what we had done last time was fine now. So since I'm writing the date, happy Lodi to all of you. Well, tomorrow we don't have tomorrow there is no class. So I'll not be taking any, but some of the classes, as I said, we will have on Tuesday from 5 to 6. I will tell you which class, so maybe not even the week after I'll not be here. So, well, 23rd January, you can plan it out if there'll be no class. I'm not around. And I'll make up for that the Tuesday after that. So on 23rd January, I'll send a note also to everyone. 23rd class will be, we will have a makeup class. Okay. So now today we will talk of and I will be covering mainly sections from section 7.1 to 7.4. There also there are some formulas which talk of shear stress, but shear stress as a function of properties. Those when we will cover, we will come to that, but let's look at this transformation. So now, what we have shown is sigma ij, this represents a state of stress at a point. And this we also call as the stress tensor. And what do we use the stress tensor for? To find the traction vector. At any orientation we want to find the surface forces, we will use sigma ij. Now, some of the books call the traction vector as the stress vector also. So we'll have these two terms, either stress and stress tensor and stress vector will have a different meaning, of course. But stress always is force per unit area. Okay? So this will always be force per unit area. So now, given x1, x2, x3 or x, y, z axis, I write the components of the stress tensor, and here I have used the fact that okay, and sometimes you'll also see this as sigma xx, these are the same notations. For shear stresses, we use tau instead of sigma. Okay? So, and this is particularly the notation in solid mechanics. And sometimes you may find that instead of they use for the normal stresses, they use only one index. So in your textbook, you will find only one index, but if you find sigma x, that is the same as sigma xx. Or if you find sigma x prime, it's the same as sigma x prime with no summation on obviously x prime. Okay. So now, if this is the phase we have, इसके नीचे चला गया क्या? Where did that note go? उड़ गया क्या? Can anyone, it seems to have just vanished, what I was writing. Any idea how to get it back? Does anyone know? 8:11 a.m. So it should be at the bottom of this. That's what I was trying to find. Anyway, I had not written too much, so I'll quickly. if suppose I have an area like this and this is the x direction. If I choose an area I choose an elemental area, the normal is in the positive x direction. So now here, what will be the stresses? The stresses on, so the traction vector here, this will be equal to sigma xxi plus sigma yxj sigma zxk. The surface force on an x face will be equal to sigma xxi plus sigma yxj, which is the same as tau yx, plus sigma zxk multiplied by the area, and the area, if it is it will be equal to delta y times delta z. So think of it as a sort of, so this face is basically so this is of ये बार-बार आज no, okay, thanks. This is the x-axis, so this is how we do this. This is x, y, z. So this is how we write this. Now, if we rotate the axis to x prime, y prime, z prime. So initially I have I keep the origin the same and so I'm just giving an example. My original axes were x, y, z. I keep z prime the same as z and rotate x and y by an angle theta. So the new axes are x prime, y prime, z prime, where z prime is the same as z and the angle between x and x prime is theta, y and y prime is theta. Is this clear? Well, now what I can do is, I can, about this x prime, maybe rotate y prime and z prime to get x double prime, y double prime, z double prime. So I can carry out any rotations about this, but I'll keep it simple. I keep it like this. Okay? So now my question is, so the new axes, old axes were x, y, z. The new axes are x prime, y prime, z prime. We know the direction cosines. That means we know how the new axes are formed with respect to the old axis. And we'll just see what they are. But then given this, the question is, and given sigma ij, can we find sigma I prime j prime, and or I can call it as, or I will call it as sigma. Instead of using the same index, I will say sigma Lm prime. So prime represents the rotated index. Okay? So now let's try to see what is sigma prime Lm. We have seen that at the start of this class in terms of sigma ij. There will be two A's. So let me write the two A's. What will be the subscript of the first one? AIL AJM sigma ij. And how we got this I explained at the start of the class. You can also have a look at it later. So that is how this is. So now if I try to work out, and I am doing this only once, rest I will leave it to you. Let's work out all the components of A. So what is A11? A11, let's have a look at this picture. Maybe I'll write this here only. Cosine of the angle between x and x prime, 1 and 1 prime. So what is that? Cosine theta. What is A12? Cosine of the angle between 1, that is x, and 2 prime, which is y prime. So what is the angle between x and y prime? 90 plus theta. So this will be equal to cosine of what is A31? Cosine of the angle between z, the old z, and 1 prime. What is that? 0, because this angle is 90 degrees. Now what is A12? Will it be equal to A21 or can it be different? A12 we have already found, sorry. A21. This will be cosine of the angle between old 2 and new 1. Old 2 is what? Y. And new 1 is what? X prime. So this will be cosine of 90 minus theta. So this will be equal to plus sine theta. Okay? And so therefore you realize the A's are not symmetric. A12 is not equal to A21. It could be, but in general they are not. And what will be A22? This will again be cosine of the angle between y and y prime. So this will be cos theta, and all other A's involving 3. A32 will be 0, A13 will be 0, A23 will be 0. What is A33? A33 will be 1. Okay? So this is how we can get this. A33 is equal to 1. All others are 0. Is that clear? So now, if I have to use this formula, all I have to do is expand this. And I will get sigma 1 prime, sigma x prime, sigma y prime, sigma z prime, and so on. All I have to do is just expand this. So now, we have worked out all the values of A. So we can now expand And if I do this, if I find sigma x prime, what I will find is this will turn out to be equal to sigma xx cos square theta plus sigma yy sin square theta and here obviously I have used tau xy is equal to tau yx. So the complementarity has been used when you expand it, and this you can try at home and you will see you will get this. Similarly, if I find sigma x prime y prime which is equal to tau x prime y prime, this will be equal to minus of sigma xx so you expand this and this is what you will get. Okay. So now what we will do is we will talk of a state of stress called two-dimensional stress or plane stress, which means where sigma xx tau xy all the stresses related to the z direction are 0, but stresses related to x and y direction are not 0. So this is what we call as a state of plane stress. And the rotation which we saw, if there we put sigma zz is equal to 0, we will get this. And that means these relations which we have derived when sigma zz was not 0. But even when it is 0, you will get the same relation because sigma zz does not appear in these relations. So now what we can also do is we can use the 2 theta relation, which is sine of 2 theta is equal to, and if we use these relations, then what we will get is sigma x prime is equal to so this is the relation which I will get. Well, from the sigma xx, if you put y, you put theta instead of theta, you put 90 plus theta, you will get sigma y prime, or you can use the transformation, and we will get tau x prime y prime is equal to minus of sigma xx minus sigma yy by 2 sin 2 theta. So here, given a state of plane stress, if I rotate the axis by an angle theta, I can find the components along x prime y prime by these relations, which are nothing but the expansion of the tensor formula. Now, of course, these relations are not sort of cumbersome to remember, but now one thing one realizes is that in a matrix, and this is for a general matrix, S11 plus S22 plus S33 is invariant. What's the meaning of invariant? That if I rotate the axis, the sum of the diagonal terms, even in the rotated axis, will be the same as what we had in the original case. So this relation follows from maths, and again, let's not go into linear algebra, but you then take it for granted. There are actually three invariants. One invariant is sum of the diagonal terms. The third one is the determinant of the matrix. And the second one is you take the first S11 times the determinant of the remaining 4 plus S22 times the determinant of the remaining 4 plus S12. So there are three invariants which come in. But let's just go by this, that sum of the diagonal terms in any matrix is invariant. So therefore, sigma xx plus sigma yy is equal to sigma x prime plus sigma y prime. Because sigma zz is 0, so therefore the sum of sigma xx plus sigma yy is this thing. So now, okay, so these which we have, what I can do is, if I look at this relation, let me call this A, let me call this B. So now, A can be rewritten as sigma x prime minus and B can be written as I've just taken in A, I've taken things on the left hand side. Now what I can do is I square and add A and B. So squaring means square each equation, each side, and then add them up. So I'll get on the left hand side, I will get sigma xx, x prime minus sigma xx plus sigma yy by 2 whole square plus tau x prime y prime square. And sigma xx plus sigma yy by 2, I can also write it as sigma x prime plus sigma y prime because that is invariant. So that will give me the left hand side. In the right hand side, what will I get? Sigma xx minus sigma yy by 2 square cos square 2 theta I will get the same term sine square 2 theta, so that will give me 1. Then I will get tau xy square sine 2 theta, sine square 2 theta plus tau xy square cos square 2 theta, that will also give me 1. Then I will get plus 2 times the first term and minus 2 times the remaining 2. And that will give 0. So when I add, what finally I am going to get is sigma x prime minus sigma xx plus sigma yy by 2 whole square plus tau x prime y prime square. This is equal to sigma xx minus sigma yy by 2 whole square plus tau xy square. And here I use this factor. So I change this to x prime. Now what is, so now I'm given sigma xy, tau xy, and I'm given an angle theta, and what I get is any x prime y prime transforms according to this equation. So this is an equation of which quantity? If I plot sigma x prime on the x-axis, tau x prime on the y-axis, what will I get? I will get a circle. Okay? And what is the center of the circle? Sigma x prime plus sigma y prime by 2, which is equal to sigma xx plus sigma yy by 2. And 0. And so this is an equation of a circle. On sigma x prime and tau so what we can say is let sigma average is equal to sigma xx plus sigma yy by 2 and let r square is equal to sigma xx minus sigma yy by 2 whole square plus tau xy square. So the right hand side I put it as r square, and whatever is the minus term in the first term I call it as sigma average. So what I have got is, so this is the equation of a circle, and now the center of the circle is equal to x-axis is and the radius is equal to r. Okay. So now if we look at this circle, what the way we are doing this is that this is sigma average, and then what I do is I have sigma xx here So sigma xx on the x-axis, tau xy on the y-axis, that gives me the state of stress for this point. And the circle which I see, the radius of this circle is what? It is sigma xx minus sigma yy by 2 whole square plus tau xy square. So now if you look at the distance from sigma average, what is sigma average? Sigma xx plus sigma yy by 2. So what's the difference from this, from sigma average to sigma xx? What is the length? It is sigma xx minus sigma xx plus sigma yy by 2. So that becomes sigma xx minus sigma yy by 2. So this basically is R. Okay, because this is sigma xx, so the sigma average is equal to sigma xx plus sigma yy by 2. Okay, and this circle which we have shown, this looks like this. Okay, now because there is symmetry about the top axis and the bottom axis, so I could have even taken this tau xy, instead of going up, I could have taken it going down. Okay, so now this is one way how we can find sigma x prime, y prime, sigma y prime, that all the points, all possible points of different values of theta will lie on this circle. Okay, now this way of, so that means the whole matrix which I have drawn, sigma I prime j prime, is represented by this circle. Different points on the circle will give me the different angles by which I am rotating the original angle. Okay, is that fine? Is it clear? अटेंडेंस चल रही है? कितनी हो गई? पूरी हो गई? अब कभी कभी मैं ऐसे आई विल डू डिफरेंट थिंग्स. One day what I am going to do is, we'll count the extra number of people and randomly I will cut out extra names. तो आपका नाम भी कट सकता है. So don't put anyone else's sign. Sometimes we'll do like what we did last time. And yet some other times I'll take a quiz. आज ले ले. ठीक है, will. Okay. So here, does everyone understand this circle? This circle represents how to find sigma x prime with respect to this thing. So now, there are certain things which happen here. So what we can do is, instead of tau xy, we can also plot minus tau xy, and this will still represent the same point. So use so now here what one sees is, so this was formalized as a method to find by a German civil engineer whose name was Otto Mohr. And he came up with this method which we call as Mohr circle for plane stress. Now, if you are in any solid mechanics course, then Mohr circle is as basic as 2 plus 2 is equal to 4. And let's see, using all these details, how do we work out this Mohr circle? So the advantage of this is that we do not have to remember the equations. So what we are given is, given sigma xx, tau yx, tau xy, sigma yy. So in a plane element, we know these four things. We know the components of the stress, the shear stress as well as the normal stresses. Of course, some of them may be zero, some of them may not be zero. So these are the four components we know, and then how do we find out? So now here, given this, if we rotate this angle element by theta and call the new axis as x prime, y prime. So we want to find out what are sigma x prime, sigma y prime, given theta. And one way is, of course, we can use the formula. Now, what is Mohr circles method? So here what we do is, now here I have assumed everything is positive. If it is negative, that means if the stress is compressive, then you have to put a minus sign. So if we are going to the right, we have to go to the left or whatever. So now let's see, first let's see it with positive. So the first thing is, we plot the point x, which is so I will go to sigma xx on the x-axis and so the right face, I call it as point x. So on this sigma tau axis, I go sigma xx and come down minus tau xy. Again, I will give you a logic when to go minus, when to go plus. But here we are assuming tau xy, the shear stress is also positive. That means on the positive face, it is acting in the positive direction. If it acts in the negative direction, then minus tau xy has to go up. Okay, because we are going minus tau xy. So this gives me point x. Second, we plot the point y, which will be sigma yy so then I find the second point. Now the second point is, on the x-axis I will go sigma yy, and on the y-axis I will go plus tau xy. It was minus for the first one, but now I go plus. So now if this is sigma yy, I will go, and this obviously, these two y things are equal in length, and this point I call as y. Is that clear? Next, what I do is, I join x and y. Okay, I take a straight line joining x and y. And join xy, and this intersects the x-axis at C. This C will be nothing but sigma xx plus sigma yy by 2. Okay? And now with Cx or Cy as the radius and C as the center, we draw a circle. With Cx, obviously my drawing is not so great. Possibly I should have used a tool which draws a circle. But with Cx or Cy as the radius, we draw a circle. Okay? Now, any point, so this is the same circle which I had drawn earlier. Okay? So now, x and y are my original points. Now, if I want to find x prime, y prime, which are rotated by an angle theta, then what I will do is, from Cx, I will rotate an angle equal to 2 theta. Because if you realize, the angle was in terms of 2 theta. So if originally I am rotating by theta, in the Mohr circle, if I rotate by 2 theta, and this point now will give me x prime, and this point will give me y prime. So if I rotate by 2 theta, then the corresponding point of the circle will give me sigma x prime and sigma y prime. I have to rotate in the same sense as, so if theta is clockwise, then 2 theta will be clockwise from original theta. If it is counterclockwise as I have done, it will be 2 theta counterclockwise. And that is how I will get different points and different states of stress. Okay? So this is how one works with Mohr circle. Now, there are two particular points, regions on the circle or specific points which are of interest. If I look at this point, if we look at points A and B, so this axis is the sigma axis, this axis is the tau axis. This I should have written earlier. Now, what is the value of tau at points A and B? See, what you will realize is diametrically 2 points opposite will represent 2 perpendicular axes. Because in this 2 theta, so if you are at 90 degrees, then in the Mohr circle we will go by 180 degrees. So any 2 diametrically opposite points will represent corresponding sigma xx and sigma yy. So what is so special about points A and B? There is no shear stress. At points A and B, we have no shear stress. And they give us the maximum and minimum normal stress. At that point, for that orientation, if I rotate, then the maximum normal stress will come when I come to this horizontal state. And this angle, so this is angle XCA we give it a special name, we call it theta p. And sigma A and sigma B, which are sigma max and sigma min, they are called principal stress. Okay? What's the meaning of principal stress? That along these directions, along these x and y, there will be no shear stress. Now, what is the importance of this in mechanics? If we look at a brittle material fails when you apply a normal stress. When that it does not fail when you apply a shear stress, or it first fails when the normal stress reaches a maximum value. So now, suppose on a brittle material like chalk, I apply only a shear force. It is shear for a particular plane, but at an inclined plane, it will correspond to tensile force. And when that tensile force reaches the maximum value the chalk can take, it will break. Do you see that? So if I'm applying only a shear force on a brittle material, it will fail. But it will fail at what? It will fail at an angle where the shear force is zero and where the tensile force is maximum. And if I look at the plane, now again, let's look at this circle. If I'm applying no shear, I'm applying only a shear force. So then sigma xx will be 0, sigma yy will be 0, tau xy on one side will be positive, on the other side will be negative. So how will the Mohr circle look like in that situation? A circle with origin as the center. So now the state of stress will be x and y will be on diametrically opposite points on the y-axis. But where will the maximum normal stress be? On the x-axis. So how much, at what angle is it in the circle? 90 degrees. So what will it be in real life? 45 degrees. So that means the failure will take place at an angle of 45 degrees if I apply if I apply a force like this. And this, you can see here, I take this, I break, and the angle, it does not break at a straight angle. It breaks at an angle, it may not be exactly 45, but closer to 45. If you want, you can take a chalk piece, try it out. But if you try to break it, maybe I'll give you a longer chalk piece. Anyone can, even you can pass it late. इसको तोड़ोगे, I'll pass, थोड़े पीछे भी pass कर दो, people can try to break it. So you can just try and maybe give the remaining pieces, एक दो पीछे, ये मत तोड़ देना भाई. So you can just try it out, and what you will see is it breaks at an angle of 45 degrees. Okay? So now here, what one sees is, if we have to find how do we find this theta p? Given sigma xx, sigma xy. So to find theta p, tau x prime y prime has to be 0. So if I put tau x prime y prime is equal to 0, I will get the relation for theta p. And this I can also get it from this angle. That angle tangent of XCA, angle XCA is theta p. So what's the tangent of this? Tangent of this is tau xy divided by this distance from x coordinate of this point to C. So therefore we can get here this will be nothing but equal to 2 tau xy divided by so one can find principal axis like this. Okay? And similarly, now क्या चीज XCA would be theta p, but tangent of 2 times angle. This is tangent of 2 times XCA because that angle is 2 theta p. No, theta p, yeah, because theta p is in the original axis. In the Mohr circle, this is 2 theta p. Okay, so in fact, maybe I wrote this wrong. This angle it's written as 2 theta. So in Mohr circle, what we go is 2 theta p. Okay, so tangent of 2 theta p is equal to this thing. इसको ठीक कर देता हूँ एक मिनट. Let me just put it correct. Okay, angle. I've made some goof up. Let's correct this. Angle XCA is equal to 2 theta p, and tangent of 2 theta p is equal to this. I think what I said there was a slight error, but this is correct now. Now what I was trying to tell you is when to go up, when to go down. When the shear stress on the face tends to rotate the element counterclockwise. So if you look at the X face or the Y face, so when it tends to rotate counterclockwise, then we go, when I have a tau yx like this. Now on this face, this tau yx and sigma xx. Now what is tau yx trying to do? Is it rotating it clockwise or counterclockwise? Counterclockwise. That means when you locate this tau, you have to go down. Now the complementary stress here is tau xy. Now what is tau xy trying to do? It is rotating it clockwise. So if it is rotating it clockwise, when you plot the corresponding point on the Mohr circle, you have to go up. So this is a way how to remember tau xy, how it goes. Okay? So now the other important point, other point is when we have so this name, we called this as point A, we call this as point B, and corresponding to this we had this one. Now C was the center, points D and D are the points where the shear stress is maximum. Okay, and this was our original X, and sorry. This was our original Y. So original stress was at X and Y, these were the original points. A and B we have already seen the points of principal stresses. Now this angle from X to D, if I call this will give me the location of maximum shear stress. Now just as I showed that the brittle material fails when the normal stress is maximum, a ductile material fails when the shear stress is maximum. So for finding the failure of a ductile material, we have to go and locate the plane where the shear stress is maximum. So now this angle XCD, this we call it as 2 times theta s. So theta s is the angle where you rotate, if you rotate the original element, you get the maximum shear. Now at the point of maximum shear, normal stress may not be 0. It will be 0 only for those specific cases when the circle lies and the diameter was on the y-axis, in that case. But otherwise, this will not be the case, and you can work out the values and you will find tangent of 2 theta s is equal to minus of sigma xx minus sigma yy by 2 times tau xy. And what is the maximum value of this tau xy shear stress? Is the radius of the circle. Okay? So that you can always find. So tau xy, this is the location, and tau xy max is equal to R. And normal stress what is the normal stress at this point where the shear stress is maximum? Sigma average. It is equal to C. It's basically, so this is equal to sigma average. And in a general case, what is the angle between theta s and theta p? What will be the, for any state of stress, the plane where you have principal stress and the plane where you have the maximum shear stress, they will vary by 90 degrees on Mohr circle. So that means 45 degrees in actual xy axis. Okay? So now, given what we have done today, we will be equipped to now find any transformation. And this is what we will have in tutorial 2. Okay? Now, certain things. Assignment 1 is due next Thursday. Assignment 1 is loaded on Moodle and it is based on tensor analysis. Now the Tuesday group will not have a tutorial. So till before the assignment is to be submitted. So please, you can discuss the assignment. Thursday is following. But फिर Tuesday's timetable वो तो ठीक है. अच्छा थर्सडे को क्लास नहीं है? अरे वाह, सुबह 8 बजे नहीं आना पड़ेगा. I also feel relieved the same way as you people do. तुम्हें आना पड़ेगा, मुझे नहीं आना पड़ेगा। मैं आई वॉज बीइंग सेल्फिश, मैं अपनी बात कर रहा था, तुम्हारी नहीं कर रहा था। ओके, सो एनीवे, बट तो असाइनमेंट का फिर कर लोगे ना अपने आप? ट्यूसडे ग्रुप एक मिनट नहीं तो अच्छा करनी का है तो फिर मंडे को कर देता हूं मैं सबमिशन। नहीं नहीं, यू हैव टू डू इट ऑन अ पीस ऑफ पेपर। आपने अच्छा वन मोर थिंग, इफ यू नीड दीज असाइनमेंट्स फॉर एग्जाम्स, मेरी ग्रेडिंग बहुत स्लो चलती है असाइनमेंट्स की, तो प्लीज कीप अ कॉपी, फोटो खींच के रख लेना आपने, ठीक है ना? मतलब आई विल ट्राई टू गिव देम एज सुन एज पॉसिबल, आई विल नॉट ग्रेड देम, दे विल बी टीएस हु विल बी ग्रेडिंग देम। सो हो सकता है असाइनमेंट का मेन पर्पज इज so that you are regular. And I don't want, as I said, no copying, you can discuss amongst yourself. So we will, the submission of assignment will be Monday then. But उसके फिर अगले थर्सडे एक और असाइनमेंट सबमिट करना होगा, उसके अगले थर्सडे मैं नहीं होऊंगा। चलो ठीक है, देखते हैं, we will decide what to do. Okay, ठीक है, अच्छा, so is this clear? अब today's lecture also